So with that, we will be sharing the slides and the recording as after we finish up here. And then also from a Q&A standpoint, as always, please do submit your questions through the webinar interface, and we will take those as we go along here. And I'll be monitoring the questions as Mike's sharing all the content, and I'll jump in with questions as you have them. So if you have questions throughout the presentation, please do submit those right away, and we'll get to those right away if we can. Otherwise, we've got time blocked in at the end for questions as well. So without further ado, I will hand over to Mike and let Mike get started.
Great. Thank you, Ryan. Good morning, everybody. Today, if you want to, where's the control here? Here we go. The topic for today is really focused on how to integrate biometric sensors into a wearable. And if you're familiar with our series of webinars in the past, there have been ones that have described the Valencell approach to doing biomonitoring, some of the common problems that are run into, signs if the project needs help, or methodologies for doing testing. Today, the approach is a little bit different. We're going to take the point of view sort of as the project team within a company that's developing a wearable, and really focus in on, with respect to integration, what questions the different members of the different functional groups will have, what challenges they're going to face, and what's the best way to sort of address those. And the format will really be to break down the project team from the product and project managers, as well as the different functional groups, and really just focus one by one the questions that they're likely to have, and then how those can be addressed. So to start with, from the point of view of the product manager or the project manager for the wearable project, oftentimes what Valencell encounters are a couple common questions. First of all, how will the overall product development process be impacted by adding biometrics? Obviously, this is important not just from a budgetary point of view, but also time to market, the overall timeline. How is that impacted by adding biometrics? Another thing is, how many design cycles are needed? When you add biosensing to a wearable, a lot of times the first iteration of a functional mock-up doesn't necessarily give you the desired performance. So how many times will this need to be iterated in order to achieve the desired performance for the end product? And then on that same note, how do I know when it's good enough? How do I know when the requirements are met from a biomonitoring perspective? And then also another question that we've seen is, well, why can't I just make my own? What's the benefits of using a pre-existing biosystem? So in order to dive into the answers to those questions, we're looking here at a slide where it's sort of a generalized product development cycle, where the top bar sort of is a perspective on the design phase, and the bottom bar is the various stages in the productization phase. And if you look at, and of course, every company is going to have a different take on this overall process, especially with respect to how the working with the contract manufacturer or ODM is arranged. But most of these blocks are accommodated in one way or the other. So first of all, when you look at how adding biosensors will impact that cycle, one of the things that we've seen over and over again is it's best to validate that form, fit, and function of the sensor in the mock-up stage. If you look at that top bar, that third box, shortly after kickoff, when you're analyzing the requirements, you're developing the whole product development plan, the test plan, you often get into some early ideation and industrial design concepts. And one of the things that we have observed is if that industrial design gets locked down too early, that can pose problems later on when the biosensors are added. So the best scenario is, in order to have a minimum impact on that product development cycle, is to front load that effort to validate the form, fit, and function of the sensor design while you are still in that mock-up stage. If you can accommodate the volume of the sensor, achieve the correct position and placement of the sensor before the overall industrial design freezes, that's the best means to have a minimal impact overall on the timeline and time to market. If the ID is frozen first and you're trying to add it later, in the end, that just ends up causing more delays as opposed to thinking about it and working through those issues up front. And that pertains mostly to many of the mechanical integration issues that one would have in order to achieve accurate biomonitoring. Another key impact to the product development cycle has to do with how biosensors are impacted by the electrical design. And the main way to minimize the impact of the product development cycle from this perspective is to have early design reviews with the sensor provider and make sure that the power supply considerations are validated before the engineering samples are built up. With respect to a sensing system, depending on the sensor, depending on the location, depending on its specifications, those are going to have different impacts on how to achieve an efficient and cost-effective power supply. And by having early design reviews and validation, you won't get into a situation where you're deep in the productization stage and you find that electrical noise is impacting sensor performance. And then if you have to then go and change a regulator, well, you might be designed into a corner and you may not be able to fit a new regulator into the design. Issues like that. So again, another recurring theme is getting involved early in that stage and making sure that the power supply is going to meet the requirements of the sensing system. That's the best means to minimize that impact to the product development cycle. Then a third area in which the biosensing will impact the development cycle is through manufacturing test. When you add these features, which really are, can be thought of as medical grade features into a consumer grade product, you really have to think through the testing from the beginning of the design. There are a lot of aspects to the optomechanics and the electronics and the integration and the assembly that could impact the ultimate performance of a unit that is mass produced that could cause it to deviate from what was achieved back during the functional alpha prototyping stage. So thinking through that manufacturing test plan in advance and then making sure that the overall means by which the product is assembled does not compromise your ability to test the biosensor at the end is very important. And so that test plan development and then also the implementation of those tests, specifically with respect to the biometrics, will likely involve some sort of custom test fixture by which the mechanics, the optics, as well as the electronics can be verified in a final article on the assembly line. And if all of these issues or these three key categories are planned for in the beginning and woven into the product development cycle, it has been our experience that the overall time to market for a given wearable, whether it's a watch or a headset, shouldn't deviate from the normal time to market of a comparable wearable that does not incorporate biometrics. The key here, obviously, is that the planning up front and the incorporation of the things that can go wrong and solving them early before steel is cut, before you're tooling, and before final board files are released for manufacture. Okay. I'll pause here for a moment for any questions that have arisen.
Doesn't look like we have any at the moment, so we'll go on.
Okay. So that sort of addresses what a typical project manager asks during the early phases of an engagement of making a biosensing wearable. This next category we're going to jump into are some of the key questions that the mechanical engineering team is likely to ask. First and foremost, what are the design rules and where can a sensor be positioned for a biometric wearable? Another is, well, what's driving the size of it? They might look at a given design and wonder if it can be made smaller. They really just have a lot of questions around what drives the size of the sensor. Also, how should that sensor be attached to the wearable? This, plays into manufacturing cost and complexity, as well as some of the use cases that are in mind, as well as immunity to certain things such as sweat ingress, which leads to that last question, which is the sensor waterproof? And that might mean that it's actually planned to be used in water, or just concern about sweat and other damage that's possible through the sensing device. So in order to look into or answer these mechanical questions, before we dive specifically into them, we're going to take a look, just as a refresher, the top 5 challenges with respect to optical heart rate monitoring sensors. Because really what we're talking about here is PPG, which is shining light into the blood and looking at the changes in that light signal and extracting parameters of interest from what is otherwise typically a very noisy signal. So in this wearable, one of the challenges, of course, is optical noise, whether it's from external sources such as ambient light or generated from internal sources such as the motion noise produced by the activity of the user. There's a few things that could be causing that. Another challenge with optical heart rate monitoring can be the skin tone. Obviously, with different chromophores and materials in the skin and blood, there can be different light transmission properties that can cause different impacts on the ability to extract a biosignal. With respect to different subjects, we're trying to monitor blood flow, so the amount of perfusion or usable signal in the blood is another challenge that we are addressing by means of the total sensing solution. Also, another challenge is dealing with the differences in the signal and noise characteristics based on the sensor location. So the answers to some of these questions are going to vary if we're talking about a hearable versus a wearable on the wrist versus maybe something else like a sensor in a helmet for a construction worker or some other device or sensing location. And then also some of the characteristic symptomatic problems of dealing with the motion noise, such as heart rate locking on to signals like the step rate when someone is running. So with that background of, those are the key challenges that one are likely to encounter, now we can dive into some of these, how these are addressed from the mechanical engineering perspective. So that first question about where can I position the sensor for a wearable and how can I get accurate signal? Well, when we talk about signal, we're really talking about a signal to noise ratio. That's the key parameter that you want to optimize from an overall system perspective. And of course, the numerator portion of that, the signal, is illustrated here in this figure. Here we're looking at some research that has been done that characterized perfusion as a function of body location, pretty much anywhere one could envision putting a wearable, from the head down to the toes. And what you see if you study these figures in depth are most of the locations that have the best PPG signal, and in this context we're calling best, that's virtually synonymous with perfusion, meaning good rich blood flow that can be interrogated by optical light. Most of those superior locations are the extremities, such as fingers, ears, and the head. Whereas some of the popular locations, such as a watch form factor, reside on limbs, which tend to have lower signal, but of course limbs can also include legs. That doesn't necessarily mean, obviously, that the use case can't be satisfied with the wearable. It just means that when in this problem overall of optimizing signal to noise ratio, you're starting with a little bit smaller number in the numerator. Your signal is a little bit inferior compared to some of the other locations. And what this means is that the sensor design and the software must be optimized to account for that smaller numerator and do some extra things from the noise perspective in order to ensure that the signal to noise ratio sufficient for the use case is achieved. So it's a lot of words to say, what's the answer to the question, where should the sensor be placed? The answer is it can be placed almost anywhere, but depending on the use case, the sensor may need to be engineered differently. The algorithms are most certainly necessary to be modified, and not all use cases can necessarily be supported at all body locations. Some common form factors such as wrist obviously can be made to work for many use cases, but in the case of other sensor locations such as the ear, that has some advantages with respect to things like CrossFit activities or really strenuous workout activities where sensors on the wrist might suffer from some of the different blood flow modulations that the ear wouldn't necessarily suffer from. Conversely, if someone is making a wearable integrated in clothing, a question might be, well, how does the signal, can you interrogate a place on the torso or on the chest or on the back? Similarly, the answer to those questions are yes, but the sensor design and the algorithms will need to be optimized for the specific signal and noise characteristics that are unique to that body position. There have been very few body positions that we've encountered that didn't provide sufficient blood flow to provide a signal, at least under certain conditions. It's really all about the use case when it comes to picking the right body position for a sensor. Good. Then next question, what's driving the sensor size? When you're making products such as hearable, obviously you want the smallest sensor possible. If you're trying to integrate on the back of a sleek smartwatch, you want as small of a sensor as possible. So it's definitely well understood that in general, a smaller sensor size is easier to work with. But in some cases, as we just saw on the previous slide, the blood flow characteristics of the region of the body of interest don't necessarily support having as small a sensor size as one would ideally like. And there's a little bit of biophysics behind the reason for this. If you look at the driving factors for sensor size, I'll point you to a couple simulations here on this slide. What we're looking at is a simulation of an optical emitter and an optical detector through some tissue and looking at blood flow. And what you observe is if the emitter can be closer to the detector, that's great for miniaturizing the sensor, but a signal-to-noise ratio is actually inferior compared to the scenario where the emitter and detector are allowed to be farther apart. So there's a very intimate relationship between the intrinsic signal-to-noise characteristics and the geometry of the overall sensor. Now, there's a lot of variables. Now, that's a general statement. There's a lot of variables and a lot of engineering that can be done to optimize within that rule, but as a guiding principle, it still stands that the farther apart they're going to be, you're getting less total light, but the ratio of good light, meaning modulated by blood flow, is superior than if they were closer together and there has not been as much volumetric interaction between the impinged light blood flow that reaches the detector. And the impact of this on a couple of different example form factors is shown on the right. For our earbud sensor module, we had talked about how the the signal quality in terms of perfusion was higher at that type of extremity, and therefore the emitter and detector are able to be a little bit closer together. Whereas if you look at the modules for the arm or wrist sensing locations, they're a little bit farther apart to account for that inferior perfusion in general across large populations of people. Okay. So moving on then from, we talked about where can a sensor be and, what drives the size of the module. Now we'll talk about integration with the housing of the wearable. So in general, there's two approaches to doing this, ultrasonic welding or gluing. And the answer, the considerations for ultrasonic welding, in the case of Valencell's benchmark solution, that frame is a molded polycarbonate, and that will ultrasonically bond very readily to another polycarbonate housing. Also, blends of polycarbonate and ABS can also work very well. However, sometimes the base of a wearable, you may not desire it to be made out of a ABS or polycarbonate material, and in such situations, that might mean ultrasonic welding is not practical. But if ultrasonic welding is chosen, what we've recommended before and had good success with is using an aluminum fixture for the part holding. Consider using a vented horn and fixture. And also, try to eliminate contact to that front lens surface. Any marring of that surface is going to compromise the optical path, which will impact the performance there. Also, a lot of consideration must be paid into tuning the parameters of the ultrasonic welding, making use of the energy directing feature. One of the concerns with ultrasonic welding in general is a vulnerability to damaging of the accelerometer. Most wearable sensors are going to have an accelerometer present to quantify activity, and the general concern will be the use of ultrasonic welding could damage those beams. So optimization of the process to avoid damaging of the accelerometer needs to be done, but it can be done with great success. But just in case something goes wrong, it's recommended to have a power on self-test. The Valencell benchmark product does have that, so in manufacturing tests, you can verify that the accelerometer survived the ultrasonic welding process. So it's recommended in any test scheme that power on self-test feature is utilized. Now, with respect to waterproofing, or the scenario where the base is not going to be PC, glue is the most likely option. And when it comes to waterproofing, it is possible that glue is actually a preferred choice. With ultrasonic welding, depending on how optimized the process is, one can actually have pinholes present, and you may not have immunity to things such as 5 atmospheres of submersion. So depending on the water resistance requirements and depending on the degree to which the ultrasonic welding process is optimized, glue could potentially be a superior choice for a waterproofing product. The one caveat is to not use a cyanoacrylate. And many times they're preferred because their curing time, but if great care is not taken to avoid, or great care is not taken in the application process, you can get some hazing of the window due to the fumes involved with that process. But in general, if the sensor would not be the weak link in any waterproofing process. There's other aspects of the system that obviously have to be taken care of in order to make sure that the overall product is waterproof, but with the proper considerations for the attachment of the sensor to the wearable, waterproof products are enabled. Okay, let me pause for a moment to see if there's any questions.
Don't see any questions come through yet. For anyone on the call, if you do have questions, please do submit those through the meeting interface, and we will we'll address those as they come in. So the ReadyTalk interface there allows questions, and submit those as they come up.
Okay, great. Okay, so moving on now. So what we spoke about earlier was sort of general across all form factors. Now we're going to dive into a couple form factor specific questions that someone on your mechanical engineering team is likely to ask during a product development stage. With respect to hearables, a question we get a lot is, what ear is better to put the sensor in? And to answer that question, I will point out that on a given individual, it is possible that one ear, there could be a little bit of asymmetry, and on an individual, one ear might have slightly better signal than the other ear. But overall, on all individuals, both ears have sufficient perfusion, and across the large population of people that we test, the average accuracy achievable with a left ear sensor is equivalent to the average ear accuracy one would get from a right side sensor. So individual differences aside, across the large populations of people, the ears are statistically equivalent. So what that means is the choice of ear for sensor placement should be driven by other product design characteristics. For instance, if you are going to have controls on an earbud, if the controls are going to be on the right earbud, well, we would recommend placing the sensor in the left side. just to minimize the amount of noise that's introduced when the user is manipulating the controls. Likewise, if it's for instance, a wireless headset like the one in the picture on the middle left, where you have a earbud and a wire that goes behind the neck to the other earbud, if there's a control box on one side, for instance, the right side, then we would encourage the designer to put the heart rate monitoring sensor on the left earbud. But in general, they both can work, and even if the sensor is placed in the earbud with the control box, it can still be made to work. These are just a guiding principle about if you have that design freedom, make use of that to give yourself the most margin for error when it comes to signal to noise. Then another question with respect to hearables is, does the sensor have to be in direct contact with the skin? Here, the general design rule is you do not have to be in direct contact with the skin, but the overall architecture of the earbud should be such that there is not a lot of relative motion between the sensor and the skin. So ideally, there would be some sort of features with, for instance, a gel cover that creates, rigidity between the sensor and the skin so that it's not allowed to flop around inside the ear. So the sensor does not have to touch it, but the earbud design should try to preserve rigidity between the sensor and the skin so that there's not a lot of, dynamic movement between the sensor and the skin. Then, when it comes to wearables, for instance, on the wrist or a forearm, the question, does the module orientation matter? Can the LEDs be in line with the axis of the forearm, or should they be perpendicular? Again, similar to the question about what ear is best, we have observed that within one individual, you can see a difference between one orientation or the other in terms of the signal to noise. But once you test across hundreds and hundreds of people, those differences average out, and in general, the conclusion is for an end product, there's not a heart rate monitoring performance-driven reason to prefer one orientation over the other. And the good thing about this is it allows you to utilize other considerations, such as ease of integration with the housing or making use of the volume, the internal volume in the product. It allows it to be driven by other considerations beyond the heart rate monitoring performance aspect. Then another question is, well, how tight must the band be? And this is a question that really has a very complex answer because there are a number of factors that play into that. It has to do with the overall size of the surface that's interacting with the arm for the wrist. For instance, if it's a large sports watch as opposed to maybe a small fitness band, that's going to impact the amount of tightness that a band should be. Also, the rigidity of the band material, whether it's stiff or has some give, that influences the answer. But the general principle is, it has to be tight enough so that it's not flopping around or loose, but not so tight that it's occluding blood. You actually can, if someone's achieving poor heart rate monitoring results with a given wearable, there's a tendency to suggest, oh, we'll just cinch it down tighter. It actually is possible that the reason the results are poor is because the band is actually too tight. One can actually occlude too much blood out from under the region of interrogation where you want to see light interacting with the blood. Okay. So that concludes sort of the most common mechanical engineering integration questions that we typically see. So now we're going to move on to another member of your engineering team, what your electrical engineers are likely to ask. Now, I will say when it comes to achieving accurate biomonitoring, the mechanical integration does tend to be the most challenging. So those questions are more complex. Their answers are more complex. There's a lot more exceptions to the rules because a lot can be achieved within the different engineering trade-offs that are available. And with that being said, that makes electrical integration seem easier by comparison. There's really only a couple questions that really influence heavily the design. What is the interface method that should be chosen? Where should the MCU be placed if it's a solution where the MCU is not within the same module as the optical sensing elements? And also, how do we ensure that the electrical noise doesn't degrade the biosensing performance? So, in order to answer those questions, we're going to start by looking at basically the block diagram of Valencell's implementation of a biosensor. What's the PerformTech processor? That's the basic MCU that does all the sensor management software. It has all of the host communication software, and it's where all of the algorithms reside that perform the biosensing functions, extract heart rate, R interval, energy expenditure, physical activity characterization. You can see that it is communicated, it communicates to the host over I2C or UART. Those are the two options. And then to the left, you see an I2C interface out to the optical detector as well as an inertial sensor, such as an accelerometer. So that first question of, well, how should we communicate to it? Should we use a UART or an I2C? Well, the general considerations that we provide are, well, first of all, it depends on the availability of the interface at your host. And that's one of the main reasons to support both of them. There are actually some host chips out there that most do have the UART, some actually do not have I2C, and vice versa. Some have I2C and some do not have UART. So really, first of all, it's what's available at the host. Then there's a power consumption consideration. In general, one expects I2C to have a little bit higher static power consumption, mainly because of the pull-up resistors when it's not in use compared to UART. But that can change depending on a lot of other factors as well. The I2C during communication, depending on things like its frequency and the length of the lines and some of the other aspects of the design, all play into that power consumption. But power consumption should be a consideration when you're choosing which design to use. Also, whether there's a preference for a clocked interface, which I2C is. Depending on whether or not the MCUs utilize crystal oscillators, that's going to, or the internal oscillators, that's going to impact the baud rate generators on the respective sides of the communication system. For instance, if the PerformTech processor, you actually have an option to omit or include an external crystal. And if you omit that external crystal, now you're relying on the device's internal oscillator for your baud rate generator. And say that one has an internal clock that's, these clocks are going to have a couple percent error from the factory. Say it errs one side low, and say the host also likewise doesn't have a crystal generating its internal baud rate, and it happens to err high. Well, now you might have a scenario where UART communications is problematic because you've found yourself into a corner case where there's variability amongst the internally generated baud rate relying on an internal oscillator. So if that was the scenario, there's not going to be an external crystal, then there's probably going to be a preference for a clocked interface. Also, likewise, UART is obviously point-to-point. If multiple peripherals are going to be on the same bus with the host, obviously you're going to want to prefer UART because you can address them individually and support multiple devices there. But that being said, a lot of designers still use UART, and in the end, a lot of times that comes down to simplicity. It's just a really, really simple interface to work with. Okay. All right. Then, on this next slide, how do we ensure that there's not going to be electrical noise from the host power supply that compromises the performance of the biosensing? Well, to start the answer to that, it helps to understand basically the dynamics of the current demand of the sensing system. While there may be an average current consumption spec, that actually can have very different peak currents depending on how the sensor is engineered, and also depending on the use case and other conditions related to how algorithms are configured. In the lower right, you can see a figure of one of our products. It's called our Benchmark RIS 2.0, where the average current consumption during the worst case scenario of heart rate monitoring is only going to be about 2 milliamps, but you can see that peak current can actually be much higher, and it occurs, at a specific, repetitive rate during the operational cycle. So first of all, managing and understanding those differences between average and peak currents and accounting for that. Isolating the power supplies and voltages from the rest of the circuit as much as possible. And then also, when using switching supplies, isolating that ground plane for the supply. And with respect to the sensing system, in many implementations, the voltage for the MCU or the sensing components, the VDD, is going to be different than the voltage that drives the LED, mainly because of the turn-on voltage of the LED, if it's a hearable or a wearable, is likely to have a different wavelength, which translates to a different turn-on voltage. And this is by no means an exhaustive list, but we have seen supplies that have been problematic, and we've seen supplies that have been used with great success. And we've listed a couple examples here from TI and Maxim of linear and buck boost supplies for a variety of different voltages that are suitable for use for VDD or VLED for applications that will enable a very straightforward achievement of the ripple voltage specs necessary to achieve good biosensing performance. But we will say that if there is voltage noise, that can be a serious issue that compromises biosensing performance. And that's why, as alluded to earlier, this aspect of the design is something that's good to validate as early as possible in the stage to finalize that bill of materials in the design. Okay. So those are the key electrical integration questions that usually prove to be most problematic. Moving on now to a different member of the team, the software. What kind of questions and issues are members of the software team likely to encounter when it comes to adding biomonitoring features to a wearable? First of all, what information has to be supplied to sensor technology in order to make it work? When you see specs on a biosensor, there's usually a big laundry list of features. A question we commonly see is, well, what is actually directly measured, and what is some sort of derived metric or assessment that's not necessarily done right on the sensor's firmware? And then furthermore, to build on that, how do you actually implement those assessments? And then finally, you have this sensor. It has a lot of features. It can do a lot of things. Well, how do I optimize its performance for my use case? The use case of, a sports headset that's only worn during a workout and does continuous monitoring of heart rate is different than, a wrist wearable with a relaxation use case. So those use cases are different, and the technology, mainly through software, needs to be optimized for performance for those different use cases. So we'll try to address each of these questions by looking at this next slide here. This slide is sort of a picture of where different layers of analysis reside when it comes to a sensing solution. If you start over on the left, you have a sensor front end. You have emitters, detector. You're acquiring raw sensor data. And typically, everything within this orange rectangle is being performed in a microcontroller or DSP within the wearable. You have signal processing occurring that's managing the sensor data, and the things that you're generating directly, and of course I use the word directly, even I'm using that a little bit loosely. What you're directly measuring is undulations and an optical light signal. Everything else you're deriving, but I'll still call it a direct measurement. Once you apply the magic of algorithms, you're directly measuring the heart rate, you're making an estimate of a VO2, you're making a measurement of an RR interval, measurement of energy expenditure, blood pressure, things like that are measured directly within the firmware out on the wearable itself. Of course, some of those metrics do have direct applicable interest to an end user, but a lot of times they need to be combined with other metrics or represented in a different way in order to create a compelling user experience, and that's where the role of assessments come in. So things like resting heart rate variability, VO2 max, cardiac efficiency, these are all assessments that make use of those metrics that are produced by the software, but those assessments can actually occur elsewhere within the software stack. So for instance, if you're using a Valencell benchmark solution, there will be app notes, and in some cases example code or demo app of how to do some of those assessments, but those will actually make use of the direct measurements that come from things output from within that orange rectangle. So in order to create that user experience, then going back to the questions, what information has to be supplied to the sensor? Well, in order to get the most accurate heart rate, some allowance should be made for the host system to pass into the firmware some specification of the activity type. Now, whether that means running or some lifestyle scenario or cycling, if that information can be provided back into the orange rectangle of the firmware, that enables the software to make some optimizations for those activities. Now, if that information is not provided, there's still going to be a default assumption made that usually is going to work well for most use cases. But a host system should have a mechanism to pass that information, if it's available, into the sensing solution. Another thing that should be passed down, if it's available, is an assessment of the subject's resting heart rate. If that information is known within the orange rectangle of firmware, that enables a more accurate estimate of energy expenditure in VO2. Likewise, if subject parameters such as weight, age, and gender can be passed in, that also enables further refinement of the outputs of those key metrics. Now, if none of that information is provided, there are still default levels that are assumed within the software, so those outputs will be generated no matter what, but they can be refined by providing those inputs down into the firmware. Another question had to do with the what's derived directly versus what is an assessment. That's trying to capture that here within this box as well. So within that orange box, the continuous heart rate, the energy expenditure, physical activity characterizations such as step rate, running, and pace, those are all measured pretty directly from the optical sensing system, in addition to with the inclusion of the accelerometer. Once those units or those measurements are available, then those can be put into assessments such as resting heart rate, which really just provides, or really it's just generated from a measurement of the heart rate over a period of time with the contextual awareness that the subject is not moving. And that contextual awareness comes from an assessment of the physical activity level. So if this is being done autonomously, that would mean that you could just measure the heart rate and measure the physical activity. And when you observe long periods of time where physical activity is zero, you can take an average of what that heart rate was and come up with some means to estimate the resting heart rate. Obviously, a true resting heart rate assessment should be done early in the morning before the subject has eaten anything or started moving around and while they're still laying in bed. That's the most meaningful measurement or time to measure their true resting heart rate. Likewise, other things such as VO2 max, that's an assessment that can be performed by combining knowledge of the heart rate, if it's known accurately, as well as distance. There are validated protocols in the literature, things like the Cooper test and Rockport test, that allow a VO2 max assessment to be performed where you step the user through a protocol, measure their heart rate, and with the known heart rate and known distance, you then can make an estimate of VO2 max. And likewise, for these other assessments, there are similar protocols that make use of the metrics. The key is, you want to avoid the garbage in, garbage out scenario. You have to have accurate input metrics in order for these assessments to be usable and enjoyed by an end user. And as far as how these are implemented, there's actually a couple ways that it can be done. Some can actually be done within the host microcontroller firmware. More often, though, they're done at the application layer on a mobile phone in some sort of application, or even in some cases in a cloud analytics offline service. But that's sort of when you see Valencell talk about various metrics, that this describes where what's measured directly from the device and what's assessed using those inputs, and then where those computations are performed.
Mike, sorry to interrupt, but we had a couple of questions come in that relate to, first question is there a location on the ear that will provide the best results, or is there a feature like flat surface that will provide the best results?
There is. We've studied that problem for years, and within the context of having a design that doesn't compromise audio quality and a design that allows an in-ear or an in-concha design, we found the sensor location at the bottom of the concha to be the best location for measuring heart rate when you factor in all of the other system considerations that a company is going to have.
Got it. Okay. Another question, would you recommend having the sensor directly on the skin or hidden behind a transparent screen?
Okay. So I'll answer that in two ways. I'm not sure if this was meant to be applied to a hearable or a wearable. So in the case of a hearable, we have done work and proven that the sensor can reside behind a transparent screen, and in some cases that's done for either aesthetic or comfort reasons, or whatever reasons the product designers had in mind. But we have validated that can be done. Whether we recommend it, we tend to think in terms of enabling the partner to be unconstrained by our impositions. So there will be some impacts. If you put a screen in front of it, you are by nature increasing that distance between the sensor and the skin, and it may be that the power consumption is going to go up because you might have to drive the LEDs a bit more to get to overcome the attenuation from the added optical path. So just knowing that most people power consumption is items number 1, items number 2, and items number 3 on their optimization list. I wouldn't necessarily recommend that, just knowing that power consumption is so important, but also we know that there's not a one-size-fits-all recommendation. If the requirements of the product are such that it's really important to have that screen, there are ways to make that work, but it's usually not a starting recommendation.
Got it. Okay. One last question's come in so far. We'll go ahead and take that one now. Where is the PerformTech processor located? Is it part of the sensor?
Okay. So actually, let me scroll back to the appropriate. There you go. I meant to address that on this screen. So that PerformTech processor, in general, for sensors in general, you do not necessarily have to have that PerformTech processor co-located with the optical detector and optical emitter. They can be separated by as much distance as the engineering of that internal I2C bus connection will allow. In other words, depending on what speed, what I2C clock speed you're going to run, and how the capacitances and inductances on that trace go, as long as the I2C communication is not compromised, it can be as far away as necessary. But in the Valencell particular products, for our benchmark RIST 1.2 product, that's a self-contained system. So the PerformTech processor is actually on the same PCBA with the detector and emitter. So the partner does not have to place that part themselves. However, for instance, on the benchmark ear solution, that MCU is not co-located on the earbuds sensor module. So the earbud sensor module is integrated in the housing, and that MCU can be placed wherever the mechanical engineers can find room to fit it, as long as that the length of that I2C trace and the design of its transmission characteristics do not compromise I2C performance.
Great.
And similarly, there's similar considerations between the PerformTech processor and the host system, whether it's a UART or I2C. As long as the communication is not compromised, there's no restriction on where it should be placed.
Got it. Great questions. Keep them coming. That's all I see for now. I think that's where we left off.
Okay. So we talked about what's measured directly and what's as an assessment. The next question that often comes from software team is, okay, how do we optimize the sensor for the use case? I've alluded to this a couple times, how there can be a variety of use cases. And as a starting point, if we take, what I'm going to say is true in general for almost any sensing solution, but I'll, as way of reference, give some specifics for Valencell's offerings. We have a PerformTech interface protocol document and a user guide. They provide the information on how you communicate with the sensor, where there's certain commands for how you activate and deactivate features, and there's certain ways you can configure the algorithm. And then with that in mind, that leads you basically to the answer to the question, how do you optimize for the use case? Well, in general, when you're talking about optimizing, you're trying to use as little power as necessary in order to deliver the features you want to your end user. So the feature activation and the algorithm configuration registers within the PerformTech technology, those are the two main methods by which power consumption is optimized in our partners' products. And there are a couple different activities or examples I can walk everyone through. First is, in a workout session, if you know you're working out, you want accurate continuous heart rate because you want those dynamics. So you're likely retrieving values once per second. You're trying to ensure that you're in the right heart rate zone. You want to see the dynamics to determine things like heart rate recovery and be able to make other assessments from the heart rate. You're activating all the physical activity metrics such as step rate, running speed, running distance, and energy expenditure, caloric burn rate. Those are done through configuration of or activation of the features and configuration of an algorithm configuration register. On the other hand, and that's also the scenario where power consumption is maximized. On the other hand, if it's a lifestyle band designed to be worn 24/7, maybe only intermittent values are needed, and maybe you don't need the continuous heart rate monitoring with all of the full strength dynamics and algorithms thrown at it. So it can be configured to be in a different activity mode, and that can help optimize for that particular use case. On the other hand, if you want to do a particular assessment that relies on HRV, the RRI is a feature that can be activated or deactivated based on the settings provided by the host controller. So all of this is basically means that the host can control the power consumption, and by careful consideration of the user experience and what features are desired, those are the knobs that the designer has, the feature activation and algorithm configuration to optimize the current consumption. All right. Then the final large bucket category is just this large bucket called testing. And this really spans two very different types of testing. But one simple question is that we are asked all the time is, how accurate is my device? Or actually, usually if you're early in the cycles, how accurate is it going to be? And then the other question is, okay, how am I going to test this in production? We've added a sensor. A lot of things happen from the time a component comes into the factory until it's getting ready to go into a box and packaging and out to the channel. How can we be sure that the biomonitoring is not being compromised? So with respect to the first question of how accurate is our device, well, I believe we actually have a whole webinar that goes into the gory details of addressing that, but I'll hit on a few of the key highlights. That in general, accuracy is never one simple number. And it's certainly not a number, it's certainly not an assessment of one person testing at one time and going by their gut feel of whether they thought it was tracking. In reality, depending on the use case, there really needs to be a specific testing protocol that's designed for the use case of the wearable. If it's a fitness product, it better encompass a lot of exercise activities, running, cycling, lifting weights, rowing, everything that people are going to do out in the real world when they're working out. If it's more of a lifestyle device, it better have a protocol that emphasizes those type of activities, because I can tell you that the types of noise that one encounters in those situations can be very different. And if you experience good luck with one device running, it doesn't necessarily mean it's going to work well when you're typing, for instance. And similarly, accuracy it's a statistical parameter. It's not subjective perception from one person. You really have to test over 30 subjects with different physical habitus, meaning different lifestyles, really fit people that are not so fit, a range of BMI. You need to have gender diversity. You have to have skin tone diversity, even hair. You have to have hair coverage diversity. When it comes to skin tone, there's a nice Fitzpatrick scale that you can use to quantify and represent that you have good coverage with respect to skin tone diversity. Unfortunately, I'm not aware of a good I'm not aware of a good standard for quantifying hair coverage, but you better have your lab team watching the wrists and ears of those people coming in and making sure that you're covering all the range that that humanity has to offer with respect to these variants. Because if the system is not optimized across all of that, then you're not going to have accuracy. So all that being said, the question still goes back, okay, so how accurate is it? Well, once you've done a lot of protocols, and once you've tested a lot of people per protocol, and once you've assumed that that group of people is not a homogeneous group of people, that it has sufficient diversity to reflect the population of end users, well then basic simple statistical analysis can be done. R-squared values are good. Bland-Altman analysis is good to assess bias and correlation. Also, there's at that point, various statistical methodologies are appropriate. What's really important is the underlying data upon which the statistical methodologies are being applied. And can't emphasize enough, lots of protocols, lots of people, because it is extremely easy to get an N=1 accurate biometric. But then, people are different, and the biometric sensor and the algorithm that worked on one person might not work on another. That's why the system has to be designed so that it works on as many people as possible, as much of the time as possible. And to do that, it requires the testing across that population. And then, of course, Valencell does this all the time, but ultimately, independent validation is the ideal scenario, and there are organizations out in the world that do independent validation and comparison with various standards for things such as heart rate. So that covers the how accurate is it. The next question is, okay, well, how do I test this sensor in production? If someone's making a headset, they probably have a test plan that they're familiar with, but now all of a sudden, if they're adding a biomonitoring feature, it's like, okay, well, how do I test that? Well, basically, during development, the design was verified. Those are often hand-built prototypes, and the form, fit, and function, the overall accuracy of the design was verified. But once you're actually making these on a factory floor with different processes, the goal is to verify that that DUT is manufactured within the specification needed to deliver the same accuracy that was observed during that design verification stage. And in order to do that, we've found that there's several categories of tests that are needed, any one of which would cause the overall system to underperform. First being electrical failures. I mean, this is obvious because if it's things like shorts and opens, a device simply doesn't work. But it can mean things that are more subtle too, such as the beam breaking in an accelerometer. It won't necessarily look like a short or an open, but it's still an electrical failure that should be tested for on every product. Optical emitter issues. There could be, it wouldn't necessarily be an open, but it could be a cold solder joint, causes very, very low optical yield for a given bias voltage. Similar, there could be issues with the detector that cause it to not perform as desired, or mechanical issues in the optical path. I talked about the hazing that could occur if certain types of glues were used in the assembly. That can be detected by a unit test in a test fixture for an end product. And in the case of Valencell, for our benchmark modules, we do 100% testing for each of those 4 failure mechanisms with a custom test system. So there's a shuttle where a device is loaded, and in a matter of about 15 seconds, a suite of tests are performed to provide coverage for all those different failure mechanisms. And then when that sensor leaves the factory and then gets integrated into an end product, we've worked with partners to make sure that that sensor can be tested again in an end product at an appropriate stage of assembly by having a partially assembled device and a customized fixture. So that's something that we found to be very beneficial in order to assure the quality of the product leaving the door. So with that being the last category, we tried to talk about how the various members of the functional team, what kind of questions they're going to ask early on during that integration process. So we tried to talk about those key questions from the mechanical point of view, the electrical point of view, the software point of view, the tester's point of view, and then the overall program manager's point of view. Those materials, those are the questions we see over and over. I hope you found those answers helpful. Do we have any more questions?
Yeah, actually, we got one other question, a couple other questions that just came in. So latest one was, have you developed a template of testing that should be conducted with the list of variables mentioned to ensure highest possibility of success? Not clear if that's related to production testing or prototype or product development testing. I think you covered the answers to that on the production side of things. So related to prototyping and product development testing, what would you say there?
We actually do. There are materials that can be shared, and I think we can follow up with the questioner here. Mm-hmm. With respect to protocols, we do have templates and a variety of protocols that cover lifestyle scenarios, strength training, high-intensity interval training, ensuring outdoor testing, and treadmill testing. We have protocols for all of those, and we're happy to share those. Similarly, for the production testing, we have specifications behind all of those different categories of tests that we share as well.
Awesome. Next question was, could you provide us an email to contact directly? So that's a perfect lead into the next slide to say thanks for your time. Really appreciate everyone taking time out of their busy schedules today to be here. But then there's Mike's email and contact info. You can also email us generally at info@valencell.com, and that will reach a group of people here that can provide the appropriate response. There was another question clarifying that previous question, so we got that. You answered that correctly. That question was referring to the test protocol on the prototyping during the product development process. And lastly, are you going to send the presentation to the participants? Yes, absolutely. We'll send that in a follow-up email, as well as this. The whole webinar has been recorded, so we will post that on our YouTube channel and send out a link to that, as well as the slides themselves. So feel free to share either the slides or the recording, or both, with any of your colleagues or anyone else who you think may be interested that was not able to attend today. So that is it as far as the questions I see coming through. Mike, thanks a lot for your time and all of the insights shared here. And thanks everyone for your attendance. We very much appreciate it. And if you do have any questions after the webinar, please do feel free to reach out either to Mike directly or to info@valencell.com, and we would be happy to answer those. So thanks again, everyone. Have a great day, and we'll talk soon.